Welcome to the 8-bit theory. In recent months, I developed a strong interest in the Commodore 128's VDC chip and its capabilities. One thing I'm really interested in is how the chip compares to other solutions of the era, mainly CGA and EGA. When you think about CGA, you probably think about weird colors. However, there were two graphics modes in CGA that allowed for 16 colors on screen. One is CGA Composite. This leverages on some of the quirks of the NTSC signal and therefore requires an NTSC display to work. The other one is CGA-Lowres. I found this so simple and interesting that I tried to display a CGA-Lowres image through the C128's VDC chip. And while I thought this would be really easy, at first it actually wasn't. Until it was again. Before I explain what CGA-Lowres is, let me share a few details about CGA and the VDC chip. Displaying 16 colors is a challenge for both the CGA and the VDC chip, but for different reasons. Both specify a resolution of 640 by 200 and a palette of 16 colors. So where's the problem? Let's look at the numbers. CGA adapters come with 16 kilobytes of video RAM. The graphics modes are 640 by 200 monochrome and 320 by 200 pixels with 4 colors, but only one color is free to choose from a total of 16. The 3 other colors have to come from one of 4 palettes, which is really 2 palettes coming in 2 intensities each. You see no 16 colors on screen. What about the VDC chip? The first C128 models came with 16 kilobytes of video RAM. The 128 DCR models came with 64 kilobytes. All 16 kilobyte models can easily be upgraded to 64 kilobytes, by the way, which is something I highly recommend. The default graphics mode is 640 by 200, but only for pixel resolution. Color resolution is actually lower. You can only set background and foreground color in blocks, and these are 8 by 8 pixels in size by default, exactly the size of a character in text mode. So for CGA the big deal is to have 16 colors displayed on screen simultaneously, and looking at the CGA palettes, this makes sense. The VDC's problem is exactly the opposite. While we can easily have 16 colors on screen at the same time, we do not have per pixel accuracy for setting the colors. And the common solution to both problems is, CGA-Lowres. The term CGA-Lowres refers to a resolution of 160 by 100 pixels and 16 colors. This is not a graphics mode that's officially documented, as it's basically the 80 by 25 text mode with a special setup. And text mode is what makes this special, because in text mode, CGA can make use of all 16 colors at the same time. We can also do 160 by 100 with 16 colors on the VDC chip, but not in text mode. And I'll start off by explaining why that is, and then I'll show how we can still achieve the same goal. As just mentioned, the 80 by 25 text mode is the basis for CGA-Lowres. The way it works is that you reduce the height of characters to 2 scan lines by writing to the encoding registers, so only the top 2 pixels of a character definition will be shown. By selecting characters that only take up the left half of a character and by setting foreground and background colors, you effectively get 2 pixels per character. For 80 characters and 100 scan lines, this results in a resolution of 160 by 100. These big pixels are really 4 by 2 pixels in size, leading up to a native resolution of 640 by 200, which is the actual screen resolution. CGA can specify background and foreground color per character. The VDC's text mode can do that for the foreground color only. The background color on the VDC chip is global for all the characters on the screen. The reason for that is that character attributes are handled differently. The attribute byte in CGA contains 4 bits for defining foreground and 3 bits for defining background colors. And I think the highest bit can be configured to either flash the character or to provide background color intensity. The VDC chip also uses a full byte to specify character attributes, and 4 bits are used for defining the foreground color just as on the CGA. There's also 1 bit for flashing the character, but the remaining 3 bits are used differently. 1 bit defines from which character set the character is to be taken, so the VDC chip can display 512 different characters on a single screen, not just 256. On the VIC-2 chip, switching the character set switches it for the full screen. On the VDC, you can switch the character set on the fly and have both character sets displayed on screen at the same time. 1 bit allows for underlining of characters, and 1 bit allows to reverse the characters, but this feature is not used. The character set for the VDC chip still holds regular and inverted character definitions, just like the character set on the C64 does. So this bit is wasted, unfortunately. Now we know that the VDC chip provides a richer feature set per character at the cost of only 1 global background color. There's a lot more to say about the text modes, but I will leave that for another video. Alright, let's talk about how we can get 160 by 100 graphics on the Commodore. And this requires switching to graphics mode. Because in graphics mode, the way how the VDC chip's attribute RAM is used changes. Graphics mode is not about characters, so we don't care about flashing and underlining. Also, we do not care about character sets. On the upside, the upper 4 bits of the attribute byte now contain 4 bits for specifying background color. On the downside, even in graphics mode, attribute RAM still doesn't relate to a single pixel. It still relates to a full block, just like in text mode. Effectively, this means we have to deal with 2 different screen layouts. On one hand, we have the screen RAM, where 1 byte sets 8 subsequent pixels. For 640 by 200, this is 128,000 bits, or in other words, 16,000 bytes. On the other hand, we have the attribute RAM, where 1 byte sets background and foreground colors for a full 8 by 8 block. For 80 by 25 blocks, this results in 2000 bytes of memory usage. For CGA-Lowres, I mentioned that characters are reduced to 2 scan lines in height. The same can be done on the VDC chip, and this also affects graphics mode. So by doing this, we can set colors on an 8 by 2 granularity instead of 8 by 8. This increases attribute RAM usage to 80 by 100 blocks, which results in 8000 bytes. The way to get us to a 160 by 100 resolution is very similar to what we do with CGA text mode, but instead of using a character that gives us the required pixel pattern, we just manually fill the pixels ourselves. Before we come to actually implementing what I was talking about, I want to introduce you to the memory map of the VDC chip and the difference to CGA. I talked about attribute bytes before. On CGA, each character takes up 2 bytes. The first byte contains the character index, the second byte is the attribute index. So both types of data are stored in an interleaved way. The VDC chip, on the other hand, strongly separates between screen memory and attribute memory. In text mode, screen memory refers to the character index, and in graphics mode, it refers to the foreground pixels. We already know that this requires 16,000 bytes of memory. Then comes attribute memory, which takes up 8000 bytes in our case. So while we are dealing with 80 bytes per line in both cases, we have 200 lines when writing the foreground pixels, but we only have 100 lines when writing the color information. I know this looks complicated, but there's a story twist just around the corner. On to programming. The best way to compare VDC and CGA is to use the same source data for display. As I was reading about CGA graphics, I stumbled across the blog at the address shown here. There, a man with a hat was shown in 160 by 100 graphics, and best of all, the image data for that is shared in a GitHub repository. So I wanted to display the same image on the C128's VDC chip. Programming the VDC chip is often referred to as being weird. While it comes with dedicated VRAM, any data you want to put in there needs to go through the VDC chip. In Commodore Basic, you have 2 system routines you can use to make VDC reads and writes happen. So for storing data into VDC memory, you have to specify the VRAM address low and high, and then either read or write from register 31. This is what needs to be done in code. As you can see, 3 basic operations are required for storing a single byte to VRAM, and this doesn't even account for calculating low byte and high byte. Not only is this very cumbersome, given the fact that you need to issue a number of basic commands for just a single operation to execute, this is really a slow way of doing things. Fortunately, there is a basic extension that helps with this, VDC-Basic. This adds new keywords to Basic 7 that make it really easy to work with the VDC chip. Here is just a quick look at the new keywords. I won't go through them in detail here, but it's worth mentioning that working with registers and copy operations can now be executed mostly through single commands. Also, copying data inside the VDC chip is possible, and this is something I'm not aware of on the CGA side of the house. We're not going to make any use of this today, but it surely allows for interesting things to be done. We'll dive into more details of these commands as we make use of them. I learned about this just a couple of months ago in Forum 64. It was published there by user McBacon already in 2013, with the last update in 2014. The original release was mentioned to have been 20 years before that, in 1993. So after about 30 years, let's not let this gem laying around any longer. First, we are taking the CGA-Lowres data file from the GitHub repository. As we want to load the file using bload, we'll need to add zeros to the beginning of the file, because bload always interprets these as the loading address of the file. We want to freely specify that address inside our code, so their value does not matter. If we didn't pad the file with leading zeros, the first 2 bytes of data would be wrongly interpreted as target address, so they would not be written to main memory and they would not be usable for us. After loading VDC-Basic into memory and activating it, we're loading CGA-Lowres dat. For specifying the address where to put the file, we read the end address of our basic program and put it there. Also, we'll need to set up the VDC chip accordingly. This is where VDC-Basic enters the stage. The RGW command does register writes. We want to reduce the number of scan lines per character to 2, which comes with quite some registers wanting to be set. And that comes with some more work to do. Register 0 just sets what's already the default value. This is in case some other program messed up the value before. Number 4 is total number of screen rows. A screen consists of more rows than what's visible to the user. The rule is that we need to have a total of 320 rows or scan lines for PAL and 264 for NTSC. I'm in PAL land, so we will go with 320. 320 must be the product of multiplying the number of total scan lines with the height of the character blocks. Right, the same blocks that define how we work with attribute RAM. We want to have 2 scan lines per block. 320 divided by 2 equals 160. For this register, the VDC chip expects a value of 1 less, so we set this to 159. Register number 6 is the number of visible scan lines. We want to have 100 visible scan lines, so we set this to 100. Next comes register 7, which is the vertical sync position. By changing the screen parameters as we did, the picture is usually shifted up or down or left or right, depending on what you did. Vertical sync position moves the picture up or down. The default value is 32 for PAL. Decreasing the value moves the picture down, increasing moves the picture up. I found this value by experimenting. We set this to 140. Finally, we're setting register number 9 to the number of scan lines per character. We set this to value 1. The VDC chip again expects a value -1 for the final value, so setting this to 1 results in a value of 2. Then we switch the chip into bitmap mode by setting bit 7 of register 25. This is done through an OR operation. VDC-Basic provides us with the function RGO for that, which makes this a no-brainer for us. Writing 2 by the power of 7 is not good performance-wise, I know, but it makes it clear that we're talking about bit 7 here. So feel free to just write 128 in your own code instead. And we'll need to tell the VDC chip to use 64 kilobytes of VRAM. While your model might come with 64 kilobytes, The kernel always initializes the VDC chip as if it only had 16 kilobytes available. 64K are enabled by setting bit 4 to 1. VDC-Basic also provides an easy-to-use memory detection routine by querying non-existing register 255. A value of 0 means 16K of VRAM, a value of 1 means 64K of VRAM are installed. The last register to set is number 36. This defines the number of memory refresh cycles for the VRAM. Refreshing takes away processing time for the VDC, so lowering this number increases rendering performance. As we reduce the scan lines per character from 8 to 2, we actually do need more rendering performance. If we didn't, the picture would look like this on a real monitor. So we set this value to 0. Then we'll clear screen and attribute RAM. VMF is for video memory fill, and that's what it does. It allows us to fill an area of VRAM with one single byte value. And we need to tell the VDC chip that attribute RAM starts at address 16,000. By default, this would be at 4096. VDC-Basic provides us with a single command to do exactly that. And we need one last preparation step. We'll create an array for mapping the byte values for colors from CGA to VDC. Black and white are similar, but all the others in between are not. Now we come to converting the image data. The CGA-Lowres data file is set to contain 2 pixels per byte. The high nibble contains the left pixel, the low nibble contains the right pixel. As mentioned earlier, this is not how the VDC lays out data in memory. We'll need to write color information into the attribute RAM and information about pixels showing background or foreground colors into screen RAM. First step is to separate high and low nibbles. The great thing about hex numbers is that each of the 2 characters represents one nibble, so we will just use mid-string and right-string to extract these. And we put these into functions for improved readability. Also, the decimal and hex string functions come in really handy for this. Let me know how you go about isolating nibbles from bytes in Commodore Basic down in the comments. I'm pretty sure there must be a more performant way to do this. So one attribute block always covers 2 pixels just as 1 byte does. The first pixel will always be the background color. If the second pixel is different, it is the foreground color. This is what we write to attribute RAM. If the second pixel is a different color, we'll also need to set the pixels to be displayed in foreground color. 15 decimal or hex 0F covers the second pixel, as that's binary 00001111. And this means background, 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 foreground, 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 foreground. And we do that twice, as the attribute block covers 2 scan lines, but the pixel we set only covers 1. That's the 2 different screen layouts I mentioned earlier. So we have to write 2 lines. Okay, let's have a look at the code. We fetch a byte from the input file, then we get background and foreground colors as decimal numbers from the functions we defined earlier. Then we convert them into hex strings and we concatenate these to create the hex string for the full byte for that. We need to do this because we need to look up the correct VDC color from the lookup table. Then we check if foreground color is different from the background color, because if it is, we need to put the 4 pixels on the right hand side of the character to be foreground pixels. This is basically optimizing the number of VRAM writes we need to do. That's pretty much it. Now let's see this in action. Loading is really quick here. I have the emulator configured for Jiffy DOS. And we see the pixels showing up already. This will take some time, so I won't show this in original speed. You might have seen that the program was asking for a data disk before switching into 2 MHz mode. I like to do this because when I'm starting the emulator from the IDE, there is no disk in the drive. So the program would terminate on a file not found error when trying to load VDC-Basic or the data file. So instead of having to type run manually, I just added a get key here with a message that gives me the time to insert the disk virtually. Of course, I could have used a different image, but it was really this image that inspired me to try this out, and I like the fact that it even says CGA on it, so there is no better way to show this, I think. And we're done. 25,000 jiffys, this is close to 7 minutes. Now, while this worked, I wish it could have been less complicated. And this is where the story twist comes in. It wasn't until weeks after I wrote this that I discovered a simpler and faster approach that was also much easier to understand. Instead of clearing the pixels in screen RAM with zeros in line number 46, we should just set all of the screen RAM to hex 0F. This way, all characters have their left 4 pixels defined as background color and their right 4 pixels as foreground color. So the if statement that checked for each single byte whether foreground pixels need to be set or not is just useless now. With the pixel setup done in one single operation before iterating through the data, we can only work with attribute RAM going forward. This improves the runtime of the conversion and rendering process from about 7 minutes to about 5 minutes, but much more importantly, it made the whole concept much easier to understand. After we're done, we just dump 8K of attribute RAM from VDC memory to the 128's main memory and write that to disk. So to display this image file, we just need to set up the VDC registers, prepare the screen RAM with hex 0F, and load the attribute RAM dump from disk. Then copy it as is to the attribute area in VRAM. And that's all that's needed for a viewer program. Now let's run this. You can see the dump files in the directory listing. VDC-Lowres, that is the full 24K dump of the first version. The other one is only attribute RAM data. And this actually is of exact the same size as CGA-Lowres stat, which was our input file. So we still need 24K of VRAM on the VDC instead of CGA 16K, but the image data itself has the same size. And once the image data is loaded, copying to VRAM is really fast, so our viewer program works. I don't know where these artifacts are coming from, must be a bad disk image. Other than that, it looks really good. This is a side-by-side comparison of the CGA and the VDC data. If you're interested in a way to compress this data, see my other video about basic microcompilers. While not a lot of games have been made for CGA-Lowres, they definitely are an interesting piece of graphics. This website here claims to know all of them, so you might want to check it out. The VDC chip is capable of much more than just displaying images. A great demo that shows software sprites is available since 2020. Also, if you're interested in a showcase of some of the VDC's graphics modes, check out the VDC Mode Mania demo. If there were more games in CGA-Lowres, they'd make for great candidates for a C128 port. Paku Paku looks really great, especially because there is also a C64 version available. So a VDC version would be a great bridge between that and the IBM-PC CGA version. And if you want to see more about programming and capabilities of CGA, you should definitely check out the PC RetroTech channel. Maybe I'll try to port one of the CGA demos there to the VDC chip one day, and in general I think I'm not yet done with the C128 challenging the IBM-PC. And that's all I wanted to show today. We got some insights into the difference between CGA and the VDC chip. They are similar in parts but still different in others. And I hope I was able to spread the word about VDC-Basic. This makes it so easy for basic programmers to leverage most of the VDC chip's power. I'll put links to everything shown in this video and some more into the description. With that being said, there's lots more to say about the VDC chip, so make sure to subscribe to this channel to not miss anything. Thanks for watching.